Okay, thank you everybody. So this is part 2 of Wireshark troubleshooting, and I apologize for the lengthy hiatus in the 2 sessions, but unfortunately a little weather system called Sandy swung by my neighborhood, and let's just say it wreaked some havoc, and things were slightly delayed. Okay, so let's get right to it. So obviously session 1 was all about how to set up Wireshark for troubleshooting. And today we're going to talk about 2 specific parts of TCP called Nagle algorithm and delayed acknowledgement. And you might say, hey, I know all about Nagle and delayed Ack, but you know what? Unless you've read the RFC, there might be a few things that you're not aware of. And for those of you who are new to the interaction between Nagle algorithm and delayed acknowledgement, there's probably a few things that might help you immediately as you troubleshoot application issues. All right, so let's get to it. And by the way, unfortunately, there's no other way to show you the interaction of Nagle and delayed acknowledgement without PowerPoint, without visualization. So we'll get right to the packet analysis, but first I wanted to show you a few slides that depict the 2 algorithms in action, because as they say, a picture's worth 1,000 words. And so the first point there is that TCP is great for a lot of things. Clearly we wouldn't have the internet as we know it if TCP wasn't invented. But when you have real-time transactions, especially that real-time transactions using small packets, TCP may not be the best choice. Okay? Or obviously TCP is in use, so some modifications to TCP need to be made at the socket level to help facilitate the communication, especially in the financial arena, financial organizations. Okay? So Nagle's motivation was to maximize the content payload. So think of this as like a bus driver sitting at the bus station that's waiting for passengers. You don't take off when the first passenger shows up. You want to sit there and wait a little bit to try and fill up the bus for obvious reasons. But at the same time, you can't sit there forever. So there are some timers involved to protect the transmission of packets. The third bullet there is delayed acknowledgement. And obviously, everybody understands delayed acknowledgement. What you may not know is that it also helps in avoiding what's called the silly window scenarios. And what's a silly window scenario? Well, imagine if you're the receiver and your window's full and you have 5 or 6, maybe 10 bytes that open up. You don't want to immediately send an acknowledgement with the Windows update saying, hey, I got 10 bytes free to go, so why don't you go ahead and send me? And then the sender is obligated to send 10 bytes. And it goes on and on and on, and obviously leads to a very inefficient transfer. So delayed acknowledgement came about to help with some of that interaction. So Nagle has its place, delayed acknowledgement has its place, but when you put the 2 together, this is when bad things can happen unless you take steps to mitigate the interaction of Nagle and delayed acknowledgement. And finally, I have a note again that if you are a financial organization, this is something that you need to look out for, because I can almost guarantee you it's on the network and it's running around and it's causing you grief. Okay? So after this session, you'll know how to spot it, how to troubleshoot it. All right, so the rules in action. This is straight paraphrase from RFCs. And before I get any further, let me give a shout out to Zoltan, who was on my old team, who helped create a lot of the content for me. All right, so Nagle rules. What does it say? Basically, if there are unacknowledged data, you need to buffer it before you can transmit. Okay, and if the data is less than the MSS, maximum segment size, you have to buffer it until it's full. Again, think of this, the bus analogy is perfect. If you're a bus, you sit at the station until you fill up with all the passengers. Unless, of course, the timer goes off, in which case you have to go. Okay. The other side of that, or similarly, when do you send data exactly? So this is outlined in RFC 1122. And if you haven't read it, I do recommend that you go through it. It's not the easiest RFC to read, but at the same time, it's not the most difficult RFC either. So I strongly recommend you to go straight to the source and read the RFC 1122. Okay? And so when do you send data exactly? Is it when you set the push bit? It's a common misconception, but it's not. Just because push bit is set doesn't mean the packet's going to go. Okay? So the first bullet is pretty obvious. If you have a full MSS, you can send the data. In other words, the bus is full, leave the station. The second one is if all data that was sent has been acknowledged and the push bit is set on a small packet, you can go. Okay. If all previous sent data has been acknowledged and the amount of data that's queued up to be sent is greater than half the send window, you're allowed to send as well. That one is a little bit esoteric. You're not going to really see that exposed anywhere in the packet, so a lot of you may not be aware of that. And where does that half factor come in? So this factor here is one of the recommended settings in the RFC, and it's implementation dependent. Okay. And the third one that you may or may not see, it's not too common, is that, especially in the modern network, is that if the push bit is set and the timer, override timer goes off, you're allowed to send the packet. Again, it's implementation dependent, and there are no hard and fast rules about what this timer should be, although the RFC has some recommendations. So again, I encourage you to read the RFC. So let's take a look at the first example. This is a buffering example, and what's important here to notice is that you have the sender on the bottom, receiver on the top, and this yellow space here represents the full packet size, or more correctly, the MSS, the maximum segment size. Okay, so let's take a look what happens. The data is being streamed. Data is being streamed again. And because 2 packets were received by the receiver, he's allowed to send an acknowledgement saying, I got the first and the second packet. Okay. More correctly, the receiver is saying, I've acknowledged all of these bytes that you've sent to me so far. That's what the acknowledgement number represents, the amount of data that I've seen from you. The other thing to note here is that these boxes down here do not represent packets. This is quantity of data that the application is giving to the TCP stack, and it's the job of TCP stack to try and fill up the entire packet so that the MSS becomes full, and then at that point you're free to, TCP is free to send the data. Okay, so some key points there to recognize. The next example is when there are unacknowledged in-flight data. And in the future sessions, we'll talk about why keeping track of in-flight data is so important. And one of the reasons is obviously with Nagle interaction, but there are other uses and other troubleshooting scenarios where the in-flight data comes in, and we'll see that in the future sessions. Okay, so the idea here is that there are data that I've transmitted that I have not seen an acknowledgement for. Okay, for whatever reason, either the round trip is too high, or the receiver was busy and haven't acknowledged me yet. So for whatever reason, I've sent some data and I've not yet seen an acknowledgement. So this is the case and how Nagle interacts in that situation. So the first packet is sent, full size, full MSS, no issues, full MSS, data is sent. At this point, if the application on the sender side has more data to send, TCP is forced to buffer that data for 2 reasons, for a couple of reasons I should say. One, it's not a full MSS yet, and number 2, timer has not gone off, and number 3, push bit hasn't been set yet. But wait, here comes the push bit. So what just happened is that the application sent this much data to the TCP stack, sent some more, maybe query results, maybe a web page, doesn't matter. And finally, the application flushed the buffer and said, here you go, I'm done. Okay, this is the last bit of what I'm going to send to you. But unlike the popular misconception that just because you set the push bit, the packet's allowed to go, because it's not a full MSS, okay, TCP is forbidden from sending that until what happens? An acknowledgement shows up. So at this point, all the data that I've sent so far has been acknowledged. Even though I have smaller than MSS, keep in mind what I just said, this is smaller than the full MSS, two conditions have been met. I now have an acknowledgement for all the outstanding data. Everything's caught up. I have a push bit set. So based on those two conditions, I'm allowed to send the data that's been buffered up so far. Okay. All right. So let's take a look at the next example. And this is when the transmit timer expires. So again, data is being sent, and I have a small packet, non-full MSS, with a push bit. But what happens? I'm forbidden from sending this because I have unacknowledged data. Okay? I haven't seen the acknowledgement for this data yet. But what if this receiver is incapable or the acknowledgement got lost? Think about that. When an acknowledgement comes back, that is an acknowledgement with no data in it, there's no reason for the receiver to know about that condition and retransmit the acknowledgement or the naked acknowledgement. And we'll go into some of that nuance of how reliable is the feedback mechanism in TCP. Okay? But suffice to say, for this scenario, let's keep it simple and just say that the data is sent. We're in the process of waiting for the receiver to send an acknowledgement yet. The application sent us a push bit, but this acknowledgement is not coming. In that case, what happens? A timer goes off, and the Nagle override timer says, you know what? I've waited long enough. I can't wait any longer, and I'm going to go ahead and send the packet anyway. Okay? So this is a case of, yes, I tried to buffer as much as possible, but a timer went off, and I can't hold on to it forever, so I'm going to go ahead and send the packet off. Okay. So now let's look at the delay. So this is the mirror situation of Nagle. Okay, so I said in the beginning that this is an interaction between Nagle and delayed ACK that causes a problem. So what's delayed ACK? Let's take a look. So data has been sent, but the receiver, the rule of TCP says, hey, I need 2 packets. And in Unix or Linux world, it's really 2 full MSS packets that I need to receive before I acknowledge. In Windows world, the Windows stack says, you know what, give me 2 packets of any size, and I'll go ahead and acknowledge it right away. So at this point, because only 1 packet has been sent, I cannot acknowledge it right away. Why? Because I don't have any data to send. Okay? As the receiver, if I had some data that I needed to send, I could go ahead and send the packet. Okay? And piggyback the acknowledgement in the data that I'm about to send. But in this case where it's unidirectional transfer, the receiver has nothing to send other than just acknowledgements for the packets that it's received. Okay? So now I'm sitting here waiting and waiting, and at some point another timer goes off, the delayed ACK timer goes off, and as a result I'm free to send the acknowledgement. And because I've received the acknowledgement, the sender can send the next data. So what is the gap here? This is the delayed acknowledgement timer. Some of the common values are 50 milliseconds, 75 milliseconds, 100 milliseconds, 150 milliseconds, or 200 milliseconds. Okay, these are what I call boundary numbers. These are numbers that show up in a trace over and over and over. We'll see some examples of that. And it should clue you in to say, you know what, I have a delayed ACK timer of 200 milliseconds that I need to contend with. Okay? All right, so now let's put all of it together. And this is the last slide, second to the last. And we'll get right down to the packet trace itself. Okay, so now we have Nagle buffering on one side, delayed acknowledgement kicking in on the receiver side. So let's take a look. So I sent the data, but as a receiver, I can't send it yet, send an acknowledgement yet. And as the sender, I cannot send the data yet because I don't have full MSS. There's no push bit set, and I have unacknowledged data, and my Nagle timer has not gone off. Okay? But to boil it down, essentially what I'm saying is that I've sent 1 packet. The receiver hasn't acknowledged yet because he wants 2 full-size packets or 2 packets. as the sender, I'm stuck because I can't send any more unless I get an acknowledgement. So we have a deadlock. So this is the Nagle-Delayed Deadlock in a nutshell. And again, I'm buffering and buffering. And now that I have a push bit, I could go ahead and send it, okay? But I still need to have an acknowledgement that comes. Okay? Keep in mind what the rule said. If I've acknowledged the data and I have a push bit, even if it's a smaller than MSS, I can send it thanks to this push bit. So the acknowledgement comes after the timer goes off and I'm free to send the data. Okay, so one more time, let's rewind the animation and take a look. Data is sent. I can't send the acknowledgement yet because it's a single packet. Okay, and my timer has gone off now. I can't send any more data because I'm waiting for it to buffer. After the delayed acknowledgement timer goes off, the receiver sends an acknowledgement, at which point the sender can send the rest of the data. Okay, so this portion right up here is the delayed ack Nagle deadlock that happens, and all this is wasted time, and this can kill throughput, as we'll see in a second. All right, so it says thank you here, but I'm going to jump right into packet analysis, which is obviously not done in PowerPoint. And if you do have any comments, I appreciate any feedback that you might have, good, bad, or otherwise. My email is shown on the screen. And just for your viewing pleasure, some pictures of my backyard when Sandy hit. So this is the day before Sandy actually made landfall. I wasn't crazy enough to be present when Sandy was there. So before you send me emails saying how stupid I am for being there, this is actually the day before Sandy hit. And obviously my neighbor here lost a chunk of real estate thanks to Sandy. And this is right outside the house where this huge tree, you can see I left the car here for perspective, what kind of damage Sandy had. All right, so let's go ahead and step right into packet analysis and take a look at the Nagle-Delayed Ack in action. And let's get to the packets. Okay, so let's take a look at the packet trace right now. What I'm going to do is start the analysis from packet number 4 here. And so because I'm starting not at packet number 1, where notice all the timers start from packet number 1, obviously, since I'm starting from midpoint or somewhere besides the first packet, what I usually like to do is I like to hit Control T to set time reference. You can also right click and set time reference, or you can hit Control T. And basically what that does, it resets the clock when the timer is involved so that everything starts from this point forward. All right, so let's take a look at this. We notice here that we have 4 packets in a row that got sent out. And if you look at the time, this time since beginning of the packet trace here, starting with my time reference, of course, you notice that all 4 packets went out in 142 microseconds. So clearly there's no delay here to speak of. And if we look at the first packet here, packet number 4, we notice that it's got 8 bytes. Okay, and the second byte is 1460, the third 1460, and the fourth packet of that packet train is 168 bytes. So it starts out with small packet number 8 bytes worth of data to full size, followed by small. Okay, now when you're doing sequence number analysis, I'm using relative sequence numbers here, you notice that so far we haven't transmitted anything and my sequence number starts with 1. I'm transferring 8 bytes, therefore my next expected sequence number, which Wireshark is nice enough to show here, is going to be 9. And so we go to the next packet. Sure enough, sequence number starts with 9. I'm going to send 1460, so my current sequence number plus the TCP length gives me the next expected sequence number of 1469. And when we go to the next packet, the third packet here in the packet train starts with 1469, another full size of 1460, gives me the next expected sequence number of 2929. So this packet number 7 here, which is the 4th packet in the packet train, should start with sequence number 2929. And in fact, that's exactly the case. 2929 going to 3097. So this is essentially sequence number analysis that we just performed, and we know that no packets went missing so far. Okay, we still don't know if we captured closer to 10 dot or if we did the packet capture closer to 192.168, but I'll show you in later sessions how to derive that type of information as well. Okay, so now remember the rule of delayed acknowledgement. It said to acknowledge every other packet. So here's our first acknowledgement, packet number 8. Which packet do you suppose the 192.168.1.1 is acknowledging? Is it going to be the first packet out of the train? No, it's not. Why? Because delayed ack says acknowledge every other packet. So it's going to acknowledge this packet. And so the next expected sequence number here was 1469, meaning I've received all the bytes up to and including 1468, and I expect you to start talking to me with byte number 1469. Okay, that's what the next expected sequence number means. So let's take a look at the acknowledgement number. Sure enough, the acknowledgement number is 1469, which was the acknowledgement number for the next packet here. It's 3097. Why? Because packet number 8 acknowledged these two packets, 4 and 5. 6 and 7 arrived. When 6 arrived, we didn't acknowledge it because it's a single packet. When 7 arrived, next expected 3097, and of course the acknowledgement number is 397. At this point, we are all caught up. There are no outstanding bytes on the wire. Okay? So that means when we look at the next packet here, there's a delta of 7 seconds. We also notice that it's a small packet, okay, 8 bytes. And again, is it coincidence that we see a transmission that starts with 8 bytes? Probably not. It might be a start delimiter of some sort, because clearly in this trace here, we notice that it started with 8 bytes as well. Okay, so now 192.168.1.1 has some data to send, and it's going to send 8 bytes. Okay, how much of this 7.2 seconds was due to Nagle preventing this packet from leaving the station? So the question is, there's 7.215 seconds of delta here. How much of it was due to Nagle, and how much of it was due to the application of the PC itself? And in this case, Nagle had nothing to do with it. Why? Because remember, there are no outstanding data in flight. All the data that has been transmitted and received has been accounted for. And because there are no outstanding data on the wire, and because this packet had a push bit set, 192.168.1.1 was free to send this the minute it had enough data here with the push bit. Okay, because there are no outstanding data on the wire. So Nagle does not come into play here, and so the entire 7.215 delay was due to application itself. Had nothing to do with Nagle. Okay, that's an important fact to keep in mind. So then what about this acknowledgement? So here in packet number 10, I sent, starting with sequence number 559 plus 8 gives me the next expected sequence number of 567. And sure enough, the acknowledgement in the packet number 11 is 567. So once again, we're all caught up. But why did it take 200 plus milliseconds for this acknowledgement to show up? If you remember from my PowerPoint animation, it said that if I receive a single packet, I cannot acknowledge it immediately. I must wait for another packet. Why? Because that's the rule of delayed acknowledgement. So here, because there was only one packet, I had to sit and wait until my delayed acknowledgement timer went off and I was able to transmit. Okay? Why wasn't it exactly 200 milliseconds? Well, I'll get into that in a second. So now that we see the acknowledgement come back, the application here, is getting ready to send 550 bytes here. Okay. In this case, why was it that 192.168 had to wait for this acknowledgement? Okay. Why didn't this packet, packet number 10 and packet number 12, go back to back? Okay. And the reason is, from 192.168 perspective, when I sent this packet, I have packets on the wire that has not yet been acknowledged, this 8 bytes here. In the meantime, as I'm waiting for this acknowledgement for these 8 bytes that I sent to come back, I'm starting to spool up how much I need to send. Okay, and in this case it's 550 bytes. But I cannot send this 550 bytes yet because Nagle says, hey, you have unaccounted for bytes on the wire. Remember, the scenario is I've sent this 8 bytes. I have not yet received the acknowledgement, which prevents me from sending any further data. Okay? Soon as I get this acknowledgement, I can now go ahead and send this small packet, 550 bytes, because 2 conditions. There are no unacknowledged data on the wire, meaning all the data has been accounted for. There's also a push bit set, and even though it's a small packet, I can go ahead and send that out. Okay. So here I have a small non-full MSS packet that went out, and in this time, let's look at the sequence number again. Next expected sequence number 1117, and sure enough the acknowledgement number is 1117, but it only took 16 milliseconds. So why is that? Why is it in packet number 10 I send a small number of packet and the acknowledgement came back after the delayed act timer went off? Why is it that packet number 12, which has similarly small non-full MSS packet, and why is it that the application was able to acknowledge it within 16 milliseconds? Because this is the artifact of piggybacking. Okay. Notice in this acknowledgement, packet number 11, we don't have any data to send to 192.168. So the only timer in play here is the delayed acknowledgement timer. When we receive packet number 12, speaking from 10.'s perspective, when we receive 192.168 1.1's data, I just so happened to have some data that I needed to send. Okay? And since I'm going to send the data anyway, I might as well go ahead and acknowledge what I've received up to that point. Okay, so that's the crucial difference between packet number 13 and packet number 11. Packet number 11 had no other data to send, so only the TCP timer was in play. Packet number 13, however, had some data that I could send, and so I piggybacked the acknowledgement, and it makes perfect sense. If I have some data to send, why not acknowledge what I've received so far? Okay. Also keep in mind that packet number 13 was able to go even though it's non-full MSS because there are no outstanding data on the wire from 10.'s perspective. 192.168 has already acknowledged everything that the 10.0 server has sent out. Okay? So because there are no unacknowledged data on the wire, and because the push bit is set, the 10.0 was able to send even a small packet. Okay. Alright, so hopefully you found this interaction of TCP delayed acknowledgement and Nagle somewhat helpful, and because you learned some of the other tidbits related to when to send data, you can better analyze trace files and try to figure out and discern where exactly the delay is coming from. Okay? It's always easier when someone leads you through these examples, so I encourage you to download this packet trace file and try to go through this step and analyze a trace file once more, and then if you have to, come back to this presentation. Okay? So once again, thank you very much, and I look forward to talking to you guys later. Bye-bye.